Hello and welcome to the Dyalog webinar. I am continuing my series on new language features in version 18.0. This is the fourth installment of my series, and in the previous the features I'm going through, you have an overview of them here. In the previous webinars, I went through all but the last 3 of these, and you can find the recording of these on dialog.tv/webinar. Now, I thought that I would do just one more webinar for the last few improved features, but when I was preparing this, I saw that there's actually quite a lot of material. So while this might look like a joke, it's actually not just one thing. It's actually 2 things, but it's using the same symbol, the same primitive. So that's what I'm going to go through, and then I'm going to have one final installment of the series in 4 weeks, where we're going to go through the last couple of things. So without further ado, here is the extended where function. So up until including 17.1, where would only take a Boolean array as its argument. And what we've done in 18.0 is to extend it to also handle numbers above 1. First, a little bit of history. So if we go all the way back to the very origins of APL, even before it was called APL, and then trace forwards, then it became a very often used from day one pattern to filter values by conditions. So using the scalar functions and scalar comparison functions especially, we would generate a mask that would indicate with 1s and 0s which values held up to a certain condition or a set of conditions combined with logical functions. And then there was the compress primitive that could be used with the Boolean mask and the actual values, and it would filter out those values based on the Boolean. Another pattern that quickly became apparent in people's code was that instead of filtering the values themselves, we would filter the indices of those values. So we get the indices of the values that live up to that requirement. And that was usually expressed with /iota row. So we are compressing the indices of the shape. In fact, Dyalog, when they introduced idiom comprehension, which means that the interpreter sees entire sequences of symbols as a single token and is optimized to handle those in one go, then /iota row was actually the prime example of something that benefits from this idiom recognition, because this is a pattern that occurs all over the place in APL style code. So the interpreter doesn't actually generate find the shape and generate the indices and then remove some of them. It directly looks at what is the Boolean vector, and then it goes in and picks out or generates those indices in the locations of the ones, assuming the shapes match, of course. So not only did we add this as an idiom, but it's more than that. It's a whole concept, the concept of converting a Boolean mask to a set of indices instead. And that's why in version 16 we added a primitive that does this. That is its job. It takes a Boolean mask and it converts it to a set of indices instead. Now, it can be used in many different ways. I'm going to go through a couple of them here. So the first thing we're going to do is we're going to use the generated indices to select things. It could be selection from the original data, from some other data. So consider this. Here's a vector of some names, some items, and then we have a selection vector, right? So this means yes, we want an apple. Yes, we want a banana. No, we don't want a cherry. Yes, we want a date, and we don't want an elderberry. And we can use compress, and that gives us just the elements that we wanted. Or we can get the indices of the elements we wanted. So apple is number 1, and so on. We can use the primitive as well. So just like we could use the compress, we can also use the indices to select with indexing instead. So this gives us the ones we're asking for. Now what's interesting with that compress was quite early on in APL's history. It was amended to not just take a Boolean vector, which would be something that comes out of a condition, but it could also take, we could also see it as having a count, and it was then renamed to replicate instead of compress. So here, the selection vector means not yes, we want an apple, but rather we want exactly 1 apple, and 2 bananas, and no cherries, and 1 date. And then we can use that with replicate, and we get what we asked for. However, if you try to use the selection vector, which is a count, with where, since where was defined as finding the ones in a Boolean array, then it would fail. It wouldn't eat numbers above 1. And what we've done in 18.0 is make the same kind of extension to where as was originally made from compress to replicate, so that this just works seamlessly as you'd expect. Now, of course, for this use case, you might say, well, I could simply use replicate. Why would I go through through a side way of indices just to get the selection? Well, a couple of things that you can do with it. One of them is if you have a larger array, a higher rank array. So here we're adding another row, and that gives us a table of ingredients. And similarly, we are amending the selection vector to become a selection matrix. And then we can say, okay, what are the indices of this selection matrix? And with this new extension of where, well, it will give you length 2 elements. And if there are duplicates, it will just have duplicated. If there are numbers above 1, you will have duplicate indices, and that means that when we use the indexing, we just get duplicated results, and this is exactly what you expect. But you can't do this with replicate. So this is an example where and to combined with indexing does something that replicate can't do, because replicate requires a vector left argument. Another thing we can do with where is to convert between representations of a set. I'll explain what I mean. Let's say that that we have a set here. So this is should we say the domain, the world that we are working in, and all sets and are then subsets of the entire domain. So we can represent a subset as a Boolean mask. In this case, it's the subset ADF. A different way of representing the exact same set is with indices. So instead of saying for each member of the full set, whether it's included in the subset or not, then we are referring to the elements of the set in their order by their indices. So it's number 1 is the A, and number 4 is the D. And when we look at it like this, then the where function becomes a conversion function to convert between the indices representation of a subset to between the mask representation of a subset to the indices representation of a subset. And similarly, if we change from using a mask to using a count, then with this extension of the where primitive, it will do the same conversion. So here we have, it's a conversion from the count representation of a multiset to the indices representation of a multiset. Well, since there is this one-to-one correspondence between the count representation and the indices representation, and the where primitive can convert the count representation to the indices representation, then you would do well in asking, how do we convert the other way around? We don't have a primitive that can take indices and convert that into a count vector or count array. And that's actually that extra hidden feature that uses the same symbol. Because, as you may be aware, we have a power operator that in certain functions is able to invert them. And so too here. If we use the where function in reverse, that does the reverse change or transformation of the representation. So we are doing where in reverse on the indices, that gives us the count. Okay, so we can use where and where inverse to convert back and forth between these things. So that's what I'll go through here. Of course, it doesn't have a name because it's not a primitive, but that doesn't mean you can't use it. It's actually really useful, and if you are to define this not using where inverse, it gets quite complicated. The first thing I'm going to show here, using the where inverse, is when we want to gather some information about some indices. So let's say we have some sorted values. They could be measurements. And we're now going to classify them into intervals, into bins, so to say. So we're using the interval index function, and that tells us that the value 3 goes in the slot between 0 and before 20, and 14 also goes between 0 and 20, and so does 15. Then we have 35 goes in between 20 and 40. Between 40 and 60 there aren't any, so that's why there's no 3 in the result. Then we have 65 in between 60 and 80, and the last two are in between 80 and 100. And what we want to find here is for each slot, so the 0 to 20 slot, the 20 to 40 slot, the 40 to 60 slot, for each slot, how many values, how many measurements went in there. Now, you might be tempted to jump to the key operator, because it does exactly this, of collecting together those that have the same value, and the right argument to the operand is the count. So this tells us, right, we had 3 1s, 1 2, 1 4, and 2 5s. Of course, these correspond to the unique values of the bins. But there's a problem here. Any bin or any interval that's not represented, Key doesn't know about it. It doesn't look at these as consecutive indices. It looks at them as values. The values could have been anything. Could have been high rank, and we would have looked at the major cells. And so because Key doesn't know what the full set, all the possibilities are, it cannot give you a count for those that are missing. So we have a missing one between 2 and 4, and we could potentially have a missing one above 5 as well. And that's where the where inverse construct comes in. So what it does is that because it's dealing with indices and it's constructing counts, then it knows that all the indices have to be consecutive. And that means if it doesn't find any 3, then it says, well, there are 0 3s there. And the way it knows how many to go up to, what's the maximum value, is simply by looking at what is the highest or last value in its argument. But we're still not done, because again, if there aren't any in the last slot up here above 100, then we don't know that, right? The inverse of where cannot look out of its argument and see what was the original list of cutoffs. Just because no values fell in those slots, then we don't have that in the argument. So what you can do is that you can use take and overtake with as many elements as you want, and that will pad with zeros at the end. So then we know that we have enough, and we have the counts for everyone. Okay, here's something else we can do with the where inverse, which is going back to booleans. There are applications that originally will give us indices, but we, for whatever reason, are interested in masks instead. So we never had a chance to look at the mask before we had the conversion, so to say. There was never any conversion. We directly computed the indices. Here's a dozen characters. With an array like this, we can, in a sense, create a map of the array, or like a signature of it, by comparing the unique elements of the array with all the elements of the array. So this loses the information about what the values are, and only keeps the information about how the individual values relate to each other. This kind of matrix can be quite useful. Ken Iverson was very fond of it. So fond that when he wrote his dictionary of APL, where he expressed his vision for what APL could and should be, he made this a primitive to create this table. So monadic equal sign, that would give you this table for any array. We can understand why it's the equal sign, because it compares the equality between all the unique elements and all the elements. It's a little bit more clear to see what's going on if we pad the matrix with headings along the left edge and the top edge. So here we can see that it's the unique elements MISP being compared to the individual elements, and you can see how they map to each other. And there are quite a few computations you can make based on this table. Now, I think this formula for adding the headings, the labels here, lends itself really nicely to a train. So, as a side note, this is how I would write it. But either way. So how would we approach creating this table while we're lacking the primitive that Iverson envisioned? Well, we can take to the key primitive, the key operator. So the key operator, again, it gives us as right argument to its operand the indices that correspond to each unique element. And so because key mixes the result, it ends up padding with zeros at the end. We can see a little bit clearer what's going on if we enclose the right argument. So we can see here that M has all the indices 1, and I has the indices 2, 5, 8, and 11, and so on. So instead of enclosing these and returning them as they are, what we can do is we can apply the where inverse on each of these right arguments. And that gives us our table. And because we're mixing, then everything gets padded correctly. That's because, of course, that there must be a 1 in the rightmost column, because the last element of the array must correspond to one of the unique elements in the array. And so we pad up until every row gets as many elements as the number of major cells in our array. And now we can maybe also begin to understand why we chose quad equals as the symbol for key. Because Iverson envisioned this kind of functionality, access to this kind of information about how individual elements relate to the unique of the elements using equal sign. So in a sense, key is the operator version of Iverson's primitive. And so the quad kind of symbolizes that it's of a more heavyweight type primitive, but otherwise doing the same thing. Now, you might ask, why would I want to use this very complicated construct of the where inverse on the right argument with the key, rather than using the much more obvious unique jot.match right tag? Well, there could be performance differences. So let's try this. We're going to run on the same data here, and we can see that even though we only had a simple array and only a dozen elements, we're already seeing a significant reduction in the time it takes to compute this. But of course, a dozen elements, that's very little, and the overall time here is very, very little. Let's step it up a little bit to 1,000 small integers. It's not even that much data. And now we can really see the difference it makes. So if you're doing this on a massive database, 1,000,000 rows, you sure want to use the right way of expressing this idea, if that's what you need. And hey, look, they even have the same length. So this is about where and where inverse. Feel free to ask questions in the chat. I'll hang around here a little bit. And while I'm waiting for this, for any questions to come in, then let's again gaze at the at all the things that we have added and improved in version 18. There's a lot of material here. Okay, so the next webinar is in 2 weeks. Richard Park is continuing an earlier webinar on the rank operator, going more in depth on how to apply it. And then I will be back in 4 weeks with the last installment of this. Now I have a question coming in. What is the difference between runtime and the CMPX function from the defense workspace? So I like using runtime because if I have any character constants, then I don't need to double all the quotes. I can put things into double quotes and I don't have to copy it in from the defense workspace. But underneath the covers, the runtime user command, which is always available otherwise, it runs the same code as CMPX. So CMPX has more complicated left argument that tells it exactly how to run, whereas the runtime user command has some more human-friendly switches and settings and so on, and you can get the help for that with runtime --. But other than that, it's basically the same. I'm getting a question as to what kind of information can we get from that matrix? Right. So one use of the matrix that Iverson was fond of, that was things that we can actually get using the key operator, and we don't need to go through this matrix to go back. But if you sum it, so then if you sum it, we go back to a count. If you sum the rows, you go back to a count of for each unique element, and you can. Let's see, what else would you use it for? You can compare you can compare various arrays and see whether they have the same kind of signature, same kind of distribution as well. Right. That's an interesting one. David is saying that if we have various types of parentheses, then yes, that's true. Then we can see. Let's say we have one row for each type of opening and closing parentheses. Then it would allow us to see an image of the parentheses depth, in a sense, and we could do computations on which level on that we are currently at for each type of parenthesis. For example, we could do that, or we could compute it separately for that. So that's something you could do. Yes. Yep, that's a good one as well. Maybe I'll have a think about what and ask around what did people used to use this for, this matrix for, and I'll get back to you in the next webinar. Okay, well, if there's nothing else, note that the schedule for the upcoming webinars has changed. We're still doing a webinar every 2 weeks, but we've moved things around a little bit, also because I need another installment of this series. So, Richard Park in 2 weeks. Hope to see you there. And otherwise, in 4 weeks, I'm continuing with the very last enhancements to the language in 18.0. Thank you so much for watching.